The final integration technique we'll be going through is integration by substitution. With integration by substitution, we will still need knowledge of the earlier integration techniques that we have learned, as integration by substitution merely transforms a complicated function into another one that is less complicated and one that we can easily integrate. Do note that if a question requires you to perform integration by substitution, the appropriate substitution will be given to you. The steps of integration by substitution are simple. We want to transform all the x terms into another variable such as theta. Referring to this quick example over here, what we have to do is to first differentiate the given substitution. So for x equals to sine theta, I can find out what is dx over d theta equals to cosine theta. And what I want to do with this is I'm going to rewrite it as dx equals to cosine theta d theta. However, do note that this last statement over here that I've written is not a legit mathematical statement, and if you are writing it, please put a pair of inverted commas over here to denote that you know it is not a legit mathematical statement. It is just for you to see what is the correct substitution to use to substitute this dx over here. Next, you will need to substitute the values of the limits, i.e. 0 and 1, into our x value here in order to find out what is the corresponding theta value. So when x is equals to 1, I know that sine theta is going to be 1, and therefore theta will be pi over 2. And when x is equals to 0, theta will correspondingly be 0. So I can change the 1 into pi over 2, and the 0 remains as a 0. And finally, once I have all these different substitutions, I can put all of them together into my transform equation, where I am going to change the limits, all the x variables, as well as the x. Let's now take a look at a few examples to help you better visualize this. In this example, I'm asked to integrate the term 1 over e to the power of 2x multiplied by square root of 1 plus e to the power of negative x. So this is a very complicated expression for us to integrate, and therefore the question has provided us with an appropriate substitution to use. So following the steps that we have gone through earlier, the first thing I'll do is to differentiate this substitution. Du over dx equals to negative e negative x over 2 square root 1 plus e negative x, which we can rewrite into, for the denominator it will be 2u, and for the numerator, if you can't see it, let's do a small change over here. U square will be equals to 1 plus e negative x, and therefore e negative x will be equals to u square minus 1, and therefore minus of e to the power of minus x will become 1 minus u square. Now the next thing we need to do is to change the limits. When x is equals to ln 2, what happens is u will become square root of 3 over 2, and when x is equals to 0, u will be equals to square root 2. So now we have all the substitutions required. Let's make all the changes. This term will become integration of 0 becomes square root 2, ln 2 becomes square root of 3 over 2, 1 over e to the power of 2x times u times, now I need to find out an expression for dx, so I'm going to do a cross multiplication over here, and that gives me 2u over 1 minus u square times du. So note that there is still this e to the power of 2x term over here which I need to transform, and what I can do now is to rewrite this term as integration of square root 2 to square root 3 over 2 e to the power of negative 2x over u times 2u over 1 minus u square du. The u's will cancel out for me here, and this e to the power of negative 2x, I can rewrite it as u square minus 1, and therefore this becomes integration from square root 2 to square root 3 over 2 u square minus 1 squared over 1 minus u square du, and we can simplify this further into square root 2 square root 3 over 2 negative of u square minus 1 du, and this term can be integrated very easily into negative 1/3 u cubed plus u, and we can do the appropriate substitutions, and I won't proceed to substitute the limits in for you. In this example, we are given an indefinite integral where there are no limits. So after we perform an integration, what happens is we will end up with a function in terms of u because we have performed a substitution. But remember that the question starts from an x, therefore we will need to have one additional step of transforming the final answer back from a function of u into a function of x. So let's carry on with the substitution. For u square equals x plus 2, I can write it as x equals to u square minus 2, and therefore dx over du will be equals to 2u, and this means that open inverted commas dx will be equals to 2u du. So now we are ready to perform the substitution. We get integration of 1 over, for x minus 2, x will be equals to u square minus 2. Therefore, x minus 2 will be u square minus 4. Multiplied by square root of x plus 2, which is just a u. And for dx, it will be changed into 2u du. And now we can do some cancellation, the u and the u. And we are left with integration of 2 over u square minus 4 du. And we can perform this integration using our MF26 formula. Remember our 1 over 2a ln of u minus a over u plus a. We can do that over here to get 2 over 2 times 2 ln of modulus of u minus 2 over u plus 2 plus c. And note that our answer now is in terms of u, which we do not want, since the question is given in terms of x, and therefore we have to simplify and do a back substitution, and that gives us 1 over 2 ln mod of square root x plus 2 minus 2 over square root of x plus 2 plus 2 plus c, and that's it. Example 3 is similar to example 2 in the sense that it is an indefinite integral and we have to do a back substitution. However, I have included this example to show you how we can do the back substitution when we are given trigonometric terms for the substitution. So for x equals to 3 over 2 sine theta, dx over d theta will be equals to 3 over 2 cos theta. And therefore, you can write it as dx equals to 3 over 2 cos theta. And we can now do all the substitutions required. So integration of square root 9 minus 4x squared dx, it will be equals to integration of square root of 9 minus 4 times 3 over 2 sine theta square times dx, which becomes 3 over 2 cos theta d theta. Now if we simplify this, the term within the square root, it becomes 9 minus 9 sine square theta, which is 9 cosine square theta, and after you apply the square root, it becomes 3 cosine theta. So this term becomes 3 cosine theta, and if we multiply by 3 over 2 cosine theta, we will end up with integration of 9 over 2 cosine square theta d theta. And as we recall, in order to integrate a cosine square, we will need to perform our double angle formula, and that gives us integration of 9 over 4 1 plus cos 2 theta d theta, which we can integrate to get 9 over 4 theta plus 9 over 8 sine 2 theta plus c. And note again that our answer is now in terms of theta, and we have to change it back into in terms of x. How we can change it is, for theta, it will simply be sine inverse 2/3 x. But what about sine of 2 theta? We cannot simply just change it into sine of 2 sine inverse 2/3 x. Okay, because this form is not a very nicely written form, so we tend to not want to use this form. And what we can do is, first, we are going to transform it slightly into using the double angle formula. So we get 9/4 sine theta cos theta. So for sine theta, no issues. Sine theta is simply 2/3 times x. But what about cosine theta? So in order for us to get a nice expression for cosine theta in terms of x, we have to make use of a right angle triangle. Okay, since I know that this angle is theta, the sides will be 2x over 3, correct? So sine theta equals to 2x over 3, which tells me that the opposite side of this angle is going to be 2x, and the hypotenuse is going to be 3. Now, if we perform the Pythagoras theorem, we will get that this adjacent side becomes square root of 9 minus 4x squared. And therefore, cosine of theta will become 9 minus 4x squared whole thing square root divided by 3. And therefore, we can rewrite our entire answer as 9/4 sine inverse 2/3 x plus 9/4 multiplied by sine theta, which is 2/3 x, multiplied by cosine theta, which is square root of 9 minus 4x squared divided by 3. And we can further simplify to combine all the different coefficients together, but I won't do that over here due to space constraints. And this is how we can perform a back substitution for any kinds of trigonometric substitutions using this right angle triangle over here.